Hello everyone, I am Usha Rani, Associate Professor in the Department of Physics. Today I am going to explain about the quantum mechanics. So, quantum mechanics are successfully explain the motion of the microscopic particles, and classical mechanics successfully explain the motion of macroscopic particles only, but it fails to explain the motion of microscopic particles. And quantum mechanics successfully explain the some of the topics like photoelectric effect, Compton effect, black body radiation. So the main contents in quantum mechanics are wave nature of particles, matter waves, properties, de Broglie hypothesis, time dependent on time independent Schrodinger wave equation, physical significance of wave function, and one-dimensional potential bonds. So here, let us see what is the nature of light. So what is the light? Is it a wave or a particle? So just what is the true nature of the light? So is it a wave or perhaps flow of extremely small particles? These questions have long puzzled scientists. So let's travel through history as we study the matter. So light is also a particle. So derived by Einstein. The theory of light being particle completely vanished until the end of the 19th century. When Albert Einstein revived it, Einstein believed light is a particle. So scientists have combined both the theory. So here, the first concept is de Broglie wavelength. So according to de Broglie wavelength, before that, the radiation exhibits a dual nature. So dual nature means here wave nature as well as particle nature. Sometimes the radiation exhibit a wave nature. So in the concept of interference, diffraction and polarization, here these concepts, the radiation exhibits a wave nature. But in the concept of photoelectric effect, Compton effect, here the radiation exhibits a particle nature. So it exhibits a dual nature. Sometimes it exhibits a wave nature and sometimes it exhibits a particle nature. But it is not possible to exhibit a dual nature at the same time. So wave is not a physical quantity and physically it cannot be seen. The main characteristics of wave is intensity, amplitude, frequency, wave velocity, wavelength. So but particle is a physical quantity. Physically it can be seen. If we apply energy or force on a particle, it moves from one place to the another place. So it can be seen through microscope. So the main characteristics of particle as mass, velocity, momentum, energy. So let us discuss about the de Broglie wavelength. The de Broglie wavelength is an important concept while studying quantum mechanics. So according to de Broglie wavelength, every moving particle is associated a wave. That wave is called as matter wave or de Broglie wave or pilot waves. So the wavelength that is associated with an object in relation to its momentum and mass is known as de Broglie's wavelength. So de Broglie wavelength is inversely proportional to its force. So de Broglie waves. What are de Broglie waves? It is said that matter has dual nature of wave particles. Previously, I told that radiation exhibits a dual nature. So that is particle nature as well as wave nature. So de Broglie waves, after the discovery Louis de Broglie, is the property of material object that varies in time or space while behaving similarly to waves. It's also called as matter waves. It holds great similarity to the dual nature of light, which behaves as a particle and as a wave that has been proven experimentally. So the objects in day-to-day life have wavelengths very small and invisible. Hence, we do not experience that. However, de Broglie wavelengths are quite visible. So here, in the concept of de Broglie wavelength and formula derivation. So, as we know that every moving particle is associated a wave, that waves are called as de Broglie waves or matter waves. But de Broglie derived de Broglie's wavelength by using the concept of Planck's quantum theory of radiation and Einstein energy mass relation. So here he also reasoned that matter would follow the same equation for wavelength as light. Lambda. Lambda is known as here de Broglie's wavelength, where de Broglie's wavelength is equal to h by p, where h is a Planck's constant, p is a momentum. So the momentum p is equal to product of mass into velocity. So the product of mass and velocity is known as momentum. So he derived de Broglie concept of wavelength, that is by using Planck's quantum theory of radiation and energy mass relation. So according to Planck's quantum theory of radiation, the energy of a photon E is equal to h nu, where h is known as Planck's constant, Nu is a frequency. And E, according to Einstein mass energy relation, E is equal to mc square. M is mass, C is a velocity of light. So from these two equations, so if the two equations combine together, we get h nu is equal to mc square, but nu is equal to c by lambda. So substitute that value, we get lambda is equal to h by mc, which is equivalent to h by lambda is equal to h by p. So if you particle is moving with the velocity v, then the momentum p, then lambda is equal to h by mv. So in the place of mv, we can substitute h by p. Then lambda is equal to h by mv or h by p. And let's go for applications of de Broglie wavelets. So as the wave properties of matter are only observed for very small objects. So as you know that previously I told that quantum mechanics successfully explained the only microscopic particles. So it is applicable for only very small objects. So that's why the de Broglie wavelength of double slit interference pattern is produced by using electrons as a source, 10 electron volts of electron. So if you substitute that value in the concept of de Broglie wavelength lambda is equal to h by mv, then we get the wavelength of de Broglie's hypothesis is 3.9 into 10⁻⁻10 meters. This is comparable to the spacing between atoms. Therefore, a crystal acts as a diffraction grating for electrons. The diffraction pattern allows the crystal structure to be determined. So, in the microscope, the size of the smallest features you can see is limited by the wavelength. With the visible light, the smallest wavelength is 400 nanometer. So, as we know, 1 nanometer is equal to 10⁻⁹ meters. So 400 nanometer becomes 4 into 10⁻⁷ meter. Okay, typical electron microscope uses the wavelength is great, smaller the can be used to study very fine details. So here we can derive the thermal de Broglie wavelength. So the thermal de Broglie wavelength can be termed as lambda suffix th is approximately the average de Broglie wavelength of the gas particles is an ideal gas at the specified temperature. The thermal de Broglie wavelength is given by the expression lambda d is equal to h by square root of 2 pi m kBt, where h is Planck's constant, we know that, and m is mass of the gas particle, kV is a Boltzmann's constant, and T is a temperature of the gas. Lambda d or lambda th is a thermal de Broglie wavelength of a gas particles. And next, I would like to explain about the Heisenberg uncertainty principle. So, in example of Heisenberg uncertainty principle for a pre-particle, so we can consider, so here we can consider momentum as well as position. So, if the momentum is completely specified, then its position is completely unspecified. If the position is completely specified and momentum is completely unspecified, so when the momentum is completely specified, we write, so we write delta p turns to 0. After that, when the position x is completely unspecified, delta x turns to infinity. So that's why here the product of two uncertainties is always greater than h cut. So delta x dot delta p is always greater than h cut. So see, here delta p turns to 0. If completely specified means delta p turns to 0. Completely unspecified means delta x turns to infinity. So delta x dot delta p is always greater than constant. So constant means that is h cut. H cut is equal to h by 2 pi. So where you know that h is the Planck's constant, the value of Planck's constant is equal to 6.625 into 10⁻⁻34 joule second. So we can write that is the Heisenberg uncertainty principle, but it is impossible to know simultaneously and with the both position and momentum of the fundamental particles. So sometimes one is specified and another one is unspecified. If another one is specified and that one is specified, so that is the delta x dot delta b is always greater than h cut. And p is equal to, as a momentum can be written as h cut into k. H cut is equal to h by 2 pi and k is equal to 2 pi by lambda. So uncertainty for Uncertainty for energy and time can be also written as delta E into delta T is always greater than or equal to h by 2 pi. Now, let us go for Schrodinger equation. For the case of one-dimensional motion, when a particle with the mass m has a potential energy, the Schrodinger equation is, for one-dimensional, we can express it as d square psi by dx square plus 8 pi square m by h square into E minus u of x into psi is equal to 0. Here, m is equal to mass, h is equal to Planck's constant, E is equal to total energy. The total energy includes a potential energy as well as kinetic energy, and U is a here, U is a potential energy. So Schrodinger equation is for basic principle for waves of a free particle is if U of x is equal to 0, that means for a free particle, there is no net force acting on it, then the potential energy becomes 0. If potential energy becomes 0 means there exists only kinetic energy. So this equation can be expressed as for kinetic energy d square psi by dx square plus 8 pi square m by h square into E psi is equal to 0. And next, let us consider for one-dimensional potential box or particle in square well. So here, for one-dimensional potential box, we have to consider square well potential. So if the particle is along moving with a one-dimensional inside the box, if particle is moving in a only inside the box means the potential energy will be 0. If particle does not cross the barriers, so consider a particle is confined to only region 0 less than or equal to x less than or equal to a. So that means in this region the potential energy is completely 0. If the particle is cross the potential walls, that means u tends to infinity, that means the potential energy will be infinity, that is we can't define. So that limits are x is equal to 0 and x is equal to a. So here, if we take the Schrodinger one-dimensional equation, as we know that d square psi by dx square plus 8 pi square m by h square into E minus u into psi is equal to 0. But here we can consider u as a 0. That is, the potential energy of the particle inside the box will be 0. Then the equation can be written as d square psi by dx square plus 8 pi square m by h square into E psi is equal to 0. So then by putting in the place of 8 pi square m by h square as k square, k is a here wave vector. So then this equation can be modified as d square psi by dx square plus k square psi is equal to 0. So, and next, here already we know that this equation, so it is looking like a second order differential equation. For second order differential equation, we can express the some boundary conditions. So if we express the boundary conditions means this equation can be taken as for the psi. Psi is a wave function. For the wave function, we can express it as a e power ikx plus b e power minus ikx. So it is the solution of the second order differential equation. So in terms of psi can be expressed as this equation, where a and b are arbitrary constants. So with the boundary conditions, if we apply boundary conditions here, then psi is equal to 0. If psi is equal to 0, psi is equal to 0 at the x is equal to 0. If psi 0 at x is equal to 0 means we get a plus b 0. If a plus b 0 means a is equal to minus b or b is equal to minus a. We substitute that value, we get psi of x is equal to a into e power ikx minus e power minus ikx. So we have the relations cos x is equal to e power ix plus e power minus ix by 2 according to mathematics, and sin x is equal to e power ix minus e power minus ix by 2 pi. So by using these relations, we can substitute psi of x can be modified as by using these conditions, and we can apply the boundary conditions. If we substitute psi of x is equal to 2ia sin kx, then we get psi of x is equal to c sin kx. So here we get with the boundary condition psi of x is equal to a. If psi of x is equal to a is also 0, psi is equal to 0 at x is equal to a. Previously psi is equal to 0 at x is equal to 0. Then we get psi, if we apply this boundary condition, we get psi of x is equal to c sin ka is equal to 0. then Ka is equal to n pi. K is equal to, we get n pi by A. So the momentum of the particle is known as momentum P is equal to mv. So by using that relation, we get also can be written as h cut into K. H cutting. Previously K is equal to, I have written as n pi by A. So substitute that value h cut into n pi by A. But the possible values of energy E is equal to P square by 2m, that is equal to pi square h cut square by 2 ma square into n square. And also it can be written as n square h square by 2 ma square also. So this is about the one-dimensional potential box. So thank you for giving this opportunity.